So far we have seen IEEE 754, that is called single precision. So we have 32 bits. Similarly, we have 64-bit representation, that is also standard IEEE 754, that is called double precision. Okay. So we have now finally single precision, double precision. So we know one thing, when we have more number of bits in in exponent and mantissa, what is going to happen? Scaling factor will be improved. That means range will be improved. Next one, accuracy will be improved. That means precision will be improved, correct? So that is what we are going to get using 64-bit. According to IEEE 754 standard, any architecture, otherwise any system. So any system has to support at least one of them. It's up to them, right? The designers can decide to implement either single precision, otherwise double precision, but at least one of them should be implemented. Okay, that is one thing you should remember about single precision and double precision. So in double precision we have more accuracy and more scaling factor. Now we will see one more important information about this IEEE 754 standard representations. So 0 and 255 are used for special purpose. That is one thing, especially in exponent field. Okay, in exponent field, if you have 0, then that has a special purpose. Similarly, 255. I am going to explain what is that special purpose, but from now onwards, don't use it. Okay, remember that point. Now, one more thing. When 0 cannot be used and 250 cannot be used, then what is the scaling factor if you see? So this is a scaling factor, 2 power minus 126 to 2 to the power of 127. That means using the exponent, what is the scaling factor you get? See, what is the minimum number you can write for exponent? Generally all zeros, right? But that is not allowed. That is for special purpose. So then for normal numbers we cannot use all zeros. Then the minimum number we can write is 0, 0, 0 followed by 1 for normal numbers. Okay. So that means what? Whenever we write 1, we know the formula for scaling factor, correct? 2 power, generally how mantissa will be evaluated, exponent will be evaluated, 2 power e minus 127, we know that. So E value is now minimum 1, maximum 254, because 255 is also not allowed for this single precision. Then if I write 1, you are going to get minus 126. That's why the scaling factor in this model is 2 power minus 126 to 2 to the power of 127. That means what? Whatever the mantissa you get, whatever the mantissa you have, then the exponent portion or scaling factor this exponent is going to provide is minus 2 power minus 126 to 2 to the power of 127. Okay, so that we should remember. Second thing. So similarly here also we have scaling factor in this double precision. We cannot use all zeros. There is no difference between single and double, only number of bits. Now we had enough stuff about this IEEE 754 models. What I would like to tell you is, what is the minimum number now you can represent for normal representations? Only 0, 0, 0 followed by 1, that means 1, 2. Maximum number we can represent, all ones are not possible, already I told you. So how many bits we have here? 11 bits for exponent. When you have 11 bits for exponent, then don't write 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 11th bit cannot be 1, right? Because all, here also same story. So 0 and here 0 comma all ones means here of course 2 to the power of 11 minus 1. That is, so tell me 2 to the power of 11 minus 1 value. 2 to the power of 11 minus 1 is nothing but 2048. 2048 minus 1, which is 2047. So if I write all ones, that is going to be 2047. That cannot be used for normal purpose. So the one less than this can be used. That's why maximum number we can write in exponent is 2046 for normal purpose. So we use 2047 for special purpose. I am going to explain. Okay. So 2046 here is the highest number we can write. So remember it, 2046. Now question is here. When you write, either you can write minimum 1 to 2046, then what is the scaling factor you are going to get? We will see. The scaling factor will be 2 power. We know the formula, right? Exponent minus 1023. Let's substitute 2 power 1 minus 1023 to 2 power 2046 minus 1023. So you get 2 power minus 1022 to 2 power 2046 minus 1023 is 2 power 1023. So this is the scaling factor. Okay. So finally you understood what is the scaling factor here and here, and especially the scaling factors are little bit varied. They are not like a regular calculation. I mean, with regular calculation you don't get a small minor modification we have to use. What is that? So we have to assume that the minimum number we can use is 1, and what is the maximum number for exponent we can use here is 126. That you should remember, because 127 cannot be used. Similarly here, the minimum number we have to use is 1, because 0 is for special purpose. Second one is the maximum number 2046. That you should remember. Okay. So that is enough. That is about single precision and double precision. There is no difference. We have here 1 bit for sine, 1 bit for sine. Here you have 7 bits for exponent. How many bits for mantissa? Recall. So here we have 8 bits for exponent, 23 bits for mantissa. 23 plus 8, 31, 31 plus 1, 32. Here we have 11 bits of exponent, 52 bits for mantissa. So more precision we get here. That's it. Now this is about comparison of single precision and double precision. And these are the scaling factors. Remember them. And here 0 and 255 are used for special purpose. Here dash are used for special purpose. 0 and dash. Recall. So 0 and 2047 are used for special purpose. Remember it. Okay.